Hi, Stu here from Music Technology, and in this video we're going to look at modifying a clean boost circuit. So you'll see some components I've got lying around here. We're going to use these to modify our circuit by adding things like diodes and some extra capacitors here and some more diodes to different places on the circuit in order to change this from a clean boost pedal into a not so clean distortion pedal. So this is one of our building blocks to building guitar circuits again. So we're going to increase the gain by tweaking this resistor here. Then we're going to use some of these different diodes, and you can see here I've got some different ones. Here's some green LEDs we can use. Here's some silicon diodes. These are 1N914s, but you can use 1N4148s. They're effectively the same thing in this circuit. And then I've got some more obscure point contact germanium diodes here, and these are D9Es. Let me also add green LEDs to this because we'll use them for experimenting. And then we're going to look at how we can arrange them asymmetrically, maybe with two on one side and one on the other side. So this is the symbol for a diode, if you hadn't worked it out already. It's like this. And we're going to talk about the characteristics of this in a minute. What we need to know for now is that this is the anode and this is the cathode, and conventional current flows through them in this direction. But if you think about it, our guitar signal's alternating current. So we want to arrange them like this so we affect each side of that cycle. So let's build it up quickly on the breadboard and listen to what it sounds like. Then we'll go back and have a look at the more technical aspects and characteristics of these different diodes. And we'll have a look on the oscilloscope as well and use a thing called XY mode so we can see some of the characteristics. So on the breadboard here, I've built up the op-amp booster circuit exactly as we had it before, with the 100K there and the 220K there, and none of these additions that I've made. And let's just check that that still sounds like a clean boost guitar pedal. Let's pick up the plectrum and I'll just play a few chords. Okay, so the very first thing we're going to do to modify this circuit is to add these diodes here, and we're just going to use silicon diodes, which is why I've laid them there. They look like this, and you can see if you look closely there's a stripe on one end, and that denotes the cathode. So I want them pointing in opposite directions, so I'm going to arrange them like this, with a stripe at one end for one and the stripe at the other end for the other. So I'm going to put them in parallel with the 220 kilo ohm resistor. So that's going to be here, and I've still got my amp and circuit powered and plugged in at the moment. It's best practice not to have your amp on or your circuit plugged in when you're doing this, I realise. Now that's not actually doing anything, and the reason it's not doing anything is because there's not enough voltage getting through these diodes to turn them on and thus clip our signal. So what we need to do is increase the gain of our circuit. Now if you remember from my previous video, we can work out the gain of the circuit using these two resistor values. So by changing a resistor value in this divider here, we can actually change the gain of the circuit. So what I'm going to do is drop this 100K to a 10K, and this time I am actually going to turn the amp off because it makes it a lot louder. And I'm going to pull this out, which is my 100K, and let's just put it over there. And I'm going to replace it with a 10K in its place. That will significantly increase the gain, and our clipping diode should work now. So we're getting what's called soft clipping there. Now you'll hear there's also some high frequency noise, especially if I let go of the strings, so I'm not grounding the guitar. Obviously I'll touch the strings, it's going to reduce that. Now one of the ways that we can reduce that is just to add a filter capacitor here. Now I won't go into why that is in this video, but in a future video I'm going to look at improvements we can make to this circuit to filter out things like noise and interference. But for now, I'm just going to put it in parallel with the diodes as it's drawn in the diagram. And I just need to turn off the amp a second while I do that. I'll put it right here, and you can see it's there and it's in parallel. Turn that back on again. And in fact, I will actually pull this out with the amp on so you can hear the difference. So it's just taking that high frequency interference, hasn't got rid of all of it, but it's just taming it a little bit. Okay, that's with our silicon diodes. Now we can try different diodes in here. So let me replace those silicon diodes with LEDs a second. I'll take out these silicon diodes and let's just use my favorite clipping LED, which is a green high brightness LED. And again, I'm going to make sure they're pointing in opposite directions. You'll note one of the LED's legs is longer than the other. Check I've got that wired up correctly. Yes, bring the amp back on again. Let's play the same chords so you can hear the difference. So that's giving you a totally different clipping sound, and it's because the characteristics of LEDs, as we'll see in a bit, are different to silicon diodes. So I'm going to go back to silicon diodes for a second. And I encourage you to experiment with these things yourself. Maybe try different color LEDs in there, different configurations. You might want to use some asymmetry like this, two going one way and one going the other. So I've put back in the silicon ones there. Turn the amp back on again. And you find these 914s or 4148s in pedals quite a lot because they do sound good in this type of circuit. They have a bit more high end than the LEDs. Now I'm going to add these diodes at the end, and I'm just going to use the same silicon diodes to begin with. But what I'm going to do is I'm going to pull out these ones. Let me add these first. So before I do that, I've actually added a 100 nanofarad capacitor here to the output, just because it's good practice to do it in this configuration. And again, we'll talk about why that is in a future video on improving the circuit. So I'm just going to turn that off. I'm going to take this capacitor out. I'm going to put in my 100 nanofarad there. And then I'm going to put this capacitor back. And then I just have to move my output across to here. Just check that works before we put in the other. Good. Right, now we're going to put in these clipping diodes into the output here. One there. And another one going in the opposite direction. Here, like this. That's with both sets of diodes in. Now let me pull out the soft clipping diodes and you can hear the difference. So you've got more harmonic content there with these output diodes. It's more of a squarish type wave, as we'll see on the oscilloscope in a minute. Now what I'm going to do on the output here is just replace these with these germanium point contact diodes so you can hear the difference that that then makes to this circuit. So go from ground to there, and this one needs to be pointing in the other direction again. So now these are germanium on the output. So that's smoothed out the sound slightly, and we can perhaps have a look at that as well on the oscilloscope in the next part. So now let's move over to the oscilloscope. We'll put through a sine wave instead, and we'll be able to see how this circuit then clips that sine wave, and we can try out the different configurations and actually see what's going on and be able to visualize it. Okay, so here we are on the oscilloscope, and I'm sending it a signal from a function generator of about 1 kilohertz. At about 151 millivolts. So you can see the division on the oscilloscope here is about 100 millivolts for the input signal. So we've got our 150 millivolts approximately, but the output signal is 1 volt, and we've got at least 1, 2, and a bit on our output. So this is a significant increase in gain, and this is without any diodes in the circuit at the moment. So this is the input and this is the output. So what I'm going to do now is I'm going to apply those soft clipping silicon diodes to my circuit over here. And there's a lot of oscilloscope probes now in the way, which is slightly hampering me in achieving that. I shall give it my best go. So I've just put in one at the moment, and you can see it's just clipped one side of the signal down here. And these are the ones in the feedback path around the op amp, and I'll put the other one in. And you can see now it's clipped the other side of that signal. Let me increase the scale of that so you can see what's going on there. So we're getting this type of clipping, and maybe if I change the time base, you can see how different that is from the original sine wave. So that's what soft clipping looks like if we feed in a sine wave. If we zoom in and scale up slightly, you'll see that specific pattern. Zoom back out again. Now what I'll do is I'll remove those diodes and I'll put the ones into the output and the hard clipping formation instead. I'll in fact just use the same diodes here to do that. So here's the first one, and we can already see that we need to reduce. And let me put in the second one, going in the opposite direction. Now we can see that clipping on the output slightly better. If I zoom in, you'll see that that is actually more of a square wave than with the soft clipping. Now what happens if we put them both in together? Let me put the diodes back in the feedback path. Here's one. And you can see this is starting to distort the waveform here. Now, if I take that one out and put the other one in, going in the other direction, you'll see the same thing happens to the other side of the waveform. So now that's moved up here to the top. But if I put in the other silicon diode in here, you'll see that we get back to that kind of waveform. And if I pull out the clipping diodes, the hard clipping diodes at the end of the circuit, doesn't really make much difference to the circuit. So it's better to use one or the other without further adjusting of the circuit. Now I'm going to take out all of the diodes again, and we end up with our huge waveform here because of the gain. And I'll put in some diodes in the op amp feedback path, going in different directions. There we are, and I'll just scale that down. So you can see not much has happened there really. If I increase the gain a bit, you'll see that clipping does occur in a similar manner, but we have to have much more gain. So I'm actually at 400 millivolts on the input now. So it's just going to clip the louder chords and signals like that, and not so much on individual notes. So let me bring that back down again to where a guitar signal usually is, around 150 millivolts for a single coil pickup anyway. Some guitar pickups can put up to a volt out. What I'll do is I'll take out these again. And now let's finally try the last thing we tried when we were playing, which was the germanium diodes on the output. So here's one. And put in the other without disturbing too many oscilloscope probes here, hopefully. So this is now the germanium, and I'm going to have to scale this up because it's clipping quite a lot. Now you can see that it's much more rounded than the silicon diodes because of the germanium material. And also I've had to increase the scale because it clips much more readily. It's got to lower for bias voltage, which we'll look at next. Before we continue, I just wanted to show you the circuit with the oscilloscope probes in. The yellow one is the input and the blue one is the output. And you can see from the image, this is what I've been doing, plugging in and taking out different diodes to show you what that looks like on the oscilloscope. So before we hop back onto the oscilloscope and look at the characteristics of a diode, let's have a look at how they're constructed. So this is a 1N914, and for audio circuits it's exactly equivalent to a 1M4148. You can use either, they're interchangeable. So let me put that next to its symbol. And you'll note the stripe on this one, which is a silicon diode, corresponds to the cathode. So we've got an anode and a cathode, denoting the more positive part of the circuit and the bit that's pointing towards the more negative part of the circuit. Now you'll note the symbol is an arrow pointing at a line, which means conventional current-wise, the direction of current is that way. And this way it comes up against this line or this wall and won't flow in this direction. So the ideal diode would let all current flow in this direction and no current flow in this direction. So it's kind of like a gate that's opening like that but won't open the other way around. So we say ideally it would have no resistance and act like a piece of wire in one direction, and in the other direction have infinite resistance and act like an open circuit. Now obviously that doesn't happen in reality because these things have tolerances like all components and will break if you go overboard with the current or the voltage going through them. They are, however, directional, and as long as we use them correctly, we can use this to our advantage. Now this diode is made out of silicon, and silicon, here's a representation of a silicon atom. It's got 1, 2, 3, 4 electrons in its shell here. But when you put it together to form this crystalline structure, it wants 8 electrons in its shell. So where does it get the other 4 from? Well, it shares them with its neighbours, and that sharing is called a covalent bond. Now you might notice there's no electrons free here to move around this structure. So how do we make it semiconduct? Well, we do that by a process called doping. To make an N-type and a P-type semiconductor, we need to dope them in different ways. So let's look at an N-type. Every now and again, we add a phosphorus atom. A phosphorus atom has a spare electron, as shown there, and that means it's free to move. But it won't move until you put a small charge onto it to make it move. Where does it go to? Well, it needs somewhere to go to, a hole to fit into. So that's where your p-type doping comes into play. And I've shown boron here, but they also use things like aluminium to do this as well. And that has one less electron, so it leaves a space for this electron to flow into, or a hole. So you can think of the hole as being positively charged and the electron as being negatively charged. So looking back at our diode here, we have a p-type region, we have an n-type region. Separating those is what's called the depletion region, and this is a gap between them. Now, as we apply voltage to this, what happens is it motivates these electrons to move, and this depletion region gets smaller to a point where there is current flow, and the electrons will hop across to there. Now, thinking of conventional current, we're thinking about it flowing in this direction. As you know, the electrons are negatively charged, so they go in this direction. So you could think of the holes as moving across if it makes it easier. Now, in a silicon diode, it needs about 0.6 to 7 volts for that to happen. Now, you can measure this yourself. If you get a multimeter, most multimeters have a diode reading mode on them, which is denoted by the diode symbol. So I'm in resistance at the moment, so if I press this, continuity, diode mode, grab my diode here, make sure my probes are around the right way, obviously, because it's directional. In fact, let me put them around the wrong way first and show you what happens. If I can actually hold this diode down to measure it. So it says OL still, which means outside of limits. But this way, I get 0.54-ish volts, so 538 millivolts is its forward bias voltage, or its point that it turns on. So that's just below 0.6 in the case of this diode. Now let's move a germanium one in here and have a look at this. So first of all, note the stripe there and the stripe there. Now let's have a look at this first of all. In this direction, I'm getting outside limit. So let me just try it in the other direction a moment. And there we go, we get to 0.215 volts, 215 millivolts, so about half of what we get for the silicon. Now note the stripes, they're a completely different way around. So on this silicon diode, the stripe denotes the cathode, but on the germanium diode, it's denoting the anode. So just be aware of that, and you can use this obviously to test that, because if you try and test it the wrong way around, it stays on outside limit. So you know the polarity of your diode as well if you use the diode tester. So we need 0.6 to 0.7, or a bit less actually in the case of that. And then with the germanium, usually 0.2 to 0.3 volts to forward bias it or turn it on. They're both affected by temperature, so you can warm them up with your finger and that will change the forward bias voltage. But in a guitar circuit, it doesn't really make that much difference to the overall effect. So what you usually see is a graph that looks a little bit like this, with this distinctive curve going up. And we've got output on the y-axis and input on the x-axis, and around 0.6 volts is where this begins to turn on and then fully comes on here. Now if we went too far in the other direction, it would drop off suddenly when it reached its reverse breakdown voltage, which broke the diode and allowed current to flow in that direction, which is what we don't want to happen ideally. You can use that sometimes. There's a specific type of diode called a Zener diode, which uses this to do things like make more accurate voltage dividers and references and things like that. Now don't take my word for it about this graph. We can actually see it on an oscilloscope using an XY mode. So what we're going to do now is we're going to move back over to the oscilloscope and have a look at that. Okay, so here I have created this very simple, what's called a curve tracer, to use my XY mode. So I've got a 10 volts peak to peak 1 kilohertz triangle wave feeding into a 50 ohm resistor, and I've got my device under test if you ever wonder what DUT means, and then I've got a 10 ohm resistor to ground here, and then I've got my 2 oscilloscope probes set up in XY mode. So that looks like this on the breadboard. Okay, so here we are on the oscilloscope now with our probes either side of our device under test, which is a silicon diode, and this is what it looks like voltage against time at the moment going through there. And we're in triangle waveform, so we are getting the top parts of the triangle, but obviously the diode's stopping the bottom parts of the triangle from happening here. But we want to see our characteristic diode response. So what we need to do is go into menu on my oscilloscope. And not all oscilloscopes have this feature, but this one does. And we want to change our time base from voltage against time to XY mode. And that makes it look like this, and I can center that up like so. So you can see that characteristic diode response there. As I bring down the amplitude of my triangle wave, you'll see I'll get to a point around here, which is our forward turn-on voltage. It was just above 0.5 volts, where it just starts to come on, and then you can see that it increases, and if I turn that back up to 10 volts, you'll see that distinctive diode characteristic there. Now I'm going to take out my silicon diode and I'm going to replace it with a germanium diode. Remembering that the stripe's on the other end in this case. So pull that out, that'll go flat. There is the germanium diode with the same diode characteristic. So we'll look more at XY mode in a future video and look at different components, but for now we're just using it to look at the diode characteristic. So hopefully that gives you some idea as to how a diode works, how it's made, and why it's clipping our AC signal, as well as a way of looking at the characteristics of a diode if you happen to have an oscilloscope. So we've looked at modifying our original circuit by replacing this 100K with a 10K to significantly increase the gain in order to employ these soft clipping diodes to clip our signal. In increasing the gain, we also increase some of the noise, so we put a 470 picofarad capacitor in here to try and tame some of that. And like I said, in a future video, we'll look at more improvements to this circuit and how to stabilize it a bit more and shield it from interference. We also looked at using diodes on the output here as hard clipping diodes, and in order to do that we also added this capacitor as best practice. Again, I'll discuss that in a future video as to why we might want a capacitor here and here. We've just looked at oscilloscope XY mode to show that characteristic diode output that looks like that you'll see on the data sheet as well. And we looked at how silicon diodes are made and how the different N and P type semiconductor material is doped. We've looked at a number of different diodes during this session. We've looked at the 1N914, which is a silicon diode, one of these. We've looked at the D9E germanium diode, which is one of these. And we also looked at the green diode to get different forms of clipping. Now you don't have to arrange them like this. You can arrange them asymmetrically with 2 on one side and 1 on the other side, both in the hard clipping circuit and the soft clipping circuit. And I'm not going to do that in this video because I want to encourage you to go away and try that for yourself and maybe comment below what type of sounds that made. You'll find that some diodes are more successful than others, but try any type of diode in these circuits and see what you get. You're not just limited to the ones that I have available today. So hopefully that helps you to use a building block that we've already discussed and begin to understand how you can modify this to get different circuits and different guitar effects out of it So we've taken a clean boost and we've turned it into a distortion circuit by using diodes to clip the signal. Now, I remember when I started, and I might have tried this on the clean boost circuit, I didn't understand enough at the time to realize why this wasn't working, and that I only needed to change this resistor value to increase the gain and thus the energy in the feedback path to make it do so. So hopefully, by building these blocks one at a time and giving you an insight into how these components work in each building block, we'll be able to over time build more complex and more stable guitar circuits, and you can then go away and start to design your own. Now, if you have any problems getting this to work, there is a previous video called Troubleshooting a Clean Boost Pedal, which is the previous one to this, and will give you some tips to getting it to work on the breadboard. As always, I'll post my notes up and I'll link them below. If you like this video, give me a thumbs up and please subscribe, because I'm going to upload more of these as we get into more complex circuits and we begin to understand how things beyond op amps work, like transistors such as JFETs, MOSFETs, traditional bipolar junction transistors, and then other components you would build guitar circuits out of, such as delay chips, PT2399 chip, and other things like that. Anyway, I've been Stu for Music Technology. Have fun experimenting with this circuit, and do post in the comments below what you found out and discovered by using different diodes. I'll catch you soon.